First of all, thank you for allowing me to talk about my research. My name is Skarleth Motino. I am currently a USRA postdoctoral researcher at the SOFIA, that is the Stratospheric Observatory for Infrared Astronomy, located in NASA Ames Center. And today I will talk to you a little bit about actually what I did for my PhD thesis, that is definition and characterization of local analogs to high-redshift galaxies. So this work is done with the collaboration of Dr. Tommy Wicklen and Dr. Rafael Eufrasio. So the motivation, basically, as we know, one of the aims of observing galaxies is to understand the evolution of the galaxies, how they assemble over time. But to observe galaxies over time, we need to actually observe different galaxies in different moments of the evolution and then put all the picture together to understand how they go evolving, right? The problem is to observe high-redshift galaxies that are the galaxies that we know for sure they are young galaxies because they are in the young universe. They are very distant, they are faint, they have irregular morphologies and they are small, but they are very difficult to observe in great detail because they basically, by the fact that they are distant, make very difficult for us to have detailed studies of these galaxies. So one way to solve these difficulties is to study local galaxies that we call local analogs to high redshift. That may have similar properties, may have similar morphologies, and we want to see if we can set a connection between this group of galaxies. So for my work, we define a sample of local analogs. This has been done in different ways previously. For instance, previous work used phi UV luminosity or H alpha equivalent width to define local analogs. In our case, what we did is we feed SEDs to the CANDLES galaxies. So CANDLES is absorbing the deep fields that cover around 160,000 galaxies and expands over redshift between 0 to 5. So what we did is we start the selection of our galaxies using the Brown 2014 galaxies. In this case, these galaxies have a lot of data that allow us to do this comparison. So we use near-infrared and mid-infrared data to feed the CD of the CANDLE galaxies. And what we found is that the best fits were given for different kind of galaxies. So if we separate the galaxies by type, we have elliptical galaxies, spheroidals, spiral galaxies, and dwarf galaxies. The dwarfs are the ones that are giving the best fits. So basically, we pick these galaxies to be our local analogs. This is not a surprise because actually dwarf galaxies have been studied to be analogs to high redshift. And in our case, all the galaxies were blue compact dwarf galaxies that are have been object of studies because they show these high star formation rates. And then these galaxies, like I mentioned, this is our sample. They are only 11 galaxies from the 129 galaxies that we compare. Only 11 give the best fits. These are low metallicity galaxies. And our goal was to study the interstellar median of these galaxies. For this, we need to characterize the dust continuum and find structural lines. So for this, we use the SOFIA telescope. So SOFIA is not a land-based telescope. It's actually a airborne telescope. So basically, it's a telescope located inside of an airborne. It has 6 different instruments. In my case, I'm focusing in using 2 instruments, that is HOP loss that is a high resolution urban wideband camera. Works between 50 to 240 microns, and the FFLS is a spectrometer that works between 42 and 210 microns. So basically, HOPLOS allows me to characterize the continuum, the dust continuum, and FFE to observe fine instruction lines, infrared fine instruction lines for these galaxies. Also, we use any archival data that we can find, like Herschel, Spitzer, Weiss, or Akari, to complement the observations. So for instance, we can see here one of our galaxies. This is NGC 2537. We see the optical, this is a Hubble image. And we also see the blue contours here come from the optical. And we see the dust emission for this particular galaxy. We see as we go farther in the infrared, we can see how the dust distribution of this galaxy is strong. So probably speaking around 150 microns. And this allows to characterize the SED of these galaxies in the far infrared. So for doing that, we're using a black body model to find the dust continuum. We're using two components because using a single component, it was not a good fit. So we're using two components, and the model is basically the addition of the two black body components. We basically are using Bayesian inference of parameters to define the best models. In this case, we're finding two black body components that are characterized by temperatures and normalizations. We're using dose emissivity that is constant. We're using 1.5 as dose emissivity. And this allows to generate the dose emission. You can see in this case, we have the peak of the emission is in the far infrared. What you see here in green is actually the Brown et al. 2014 spectra data, that is the near infrared, mid infrared. And we basically, what we find is just the interaction between the Brown data and our models are fit very well. And then we have Herschel and SOFIA data in this area, in the far infrared. And this allows to derive the far infrared or total infrared luminosity very well. This is important because these measurements are used for reference for high redshift galaxies. So it's very good to have a well-defined far infrared luminosity. And well, here is just all the models for all the galaxies in this case. And what we found in general is that these galaxies tend to have like a warm dust component. We're comparing here with the Kingfish galaxies and the Dwarf galaxy survey of Maiden 2013. And we find that our galaxies have a warmer component. And also we're using the lighting package. This is actually one more of my collaborator, Eufrasio 2017, where he, this package allows to fit the star formation histories of these galaxies and to find the SED for the UV up to the far infrared for these galaxies. So what you can see here in the right is the SED that we produce for these galaxies. We're basically using Drainelli models that are incorporated.
You have 1 minute left.
Okay.
1 minute left.
Thank you. So I'm gonna move a little bit just to the star formation histories. What is important for us is to observe that the galaxies that we found, we can define star formation histories using the fitting of the SED. And some of these galaxies, they show that they have a star formation that can be traced in the last 1 giga year. So we're finding these galaxies that have very short star formation history, and we think these galaxies are actually young galaxies in the nearby universe. So that's why it's important to study these kind of galaxies. And I just gonna stop with the summary. I'm sorry for that. We need more information about these kind of galaxies, and we hope that with James W. Webb, we can actually observe the near infrared and near-infrared, these kind of galaxies that can be very important for high redshift observations too. Thank you.